Hello everyone. In this video, we will be talking about rotational kinematics. So far, we've been considering linear motion, where we look at displacement x, acceleration, or velocity, and time. Now, these apply to a linear picture, where we see the motion of an object as a change in position from point A to some position, point B. But how does this apply to rotation? So let's say we have an object like this marker, and there's an axis going through the center of this marker, and this marker is being rotated. How do we analyze motion of a rotating object like this? Now, if we could look at the picture from the top of the marker, we see the marker rotating as a motion of the marker rotating in this direction. In linear motion, we looked at the change in position. When we're considering rotation, we imagine an imaginary point A as the beginning of the motion and a final point B at the end of the motion. Change from point A to point B is what we see as displacement and rotation. The object itself doesn't change position, but point A that we imagine moves to a point B after the rotation. So we look at the angle between point A and point B. This angle is what we see as displacement. When we're considering rotation, we consider this x and y axis, and we see and compare and reference motion to this point on the positive x-axis. Positive motion is in the direction of counterclockwise, whereas negative motion is in the direction of clockwise. Now, seeing this, we can find equivalence of linear variables in terms of rotation. So, where we have displacement, we have a change in angle as our displacement. Acceleration becomes angular acceleration. Velocity becomes initial velocity, final velocity, as angular initial velocity and angular final velocity. And finally, time remains the same. So, nothing but the symbols for our kinematic variables have changed so far. Now, we can move from linear to rotation or rotation from linear. What does that mean? So, if we wanted to find linear acceleration, let's say if the object is accelerating in this direction, the acceleration will be the angular acceleration times the radius, or the distance from the center axis of the point. Similarly, velocity will be angular velocity times the radius. Now, what about our most important tool when we're considering kinematics, our kinematic equations? Again, all we change are the variables in place of the equations. So, for example, let's look at v equals v naught plus at. If we change the variables for rotation, we'll get final angular velocity equals initial angular velocity plus angular acceleration times time. And this holds for all of the kinematic equations that we've used. Let's look at an example problem. Let's consider this example. Let's say we have a centrifuge that is initially at rest and then is accelerated to 10,000 RPM in 200 seconds. We want to know the acceleration, or the angular acceleration, for the centrifuge. So let's get started. First, let's list out all of the known variables. We have an initial angular velocity of 0 RPM, so 0 radians per second. We have a final angular velocity of 10,000 RPM. Now, we want to change this to our SI units when we're considering rotation, so radians per second. How do we go from revolutions to radians? Each revolution is a change of 2 pi radians. So 10,000 times 2 pi, and as we want seconds, we'll divide this by 60 to get radians per second, which will be 1047.2 radians per second as our final angular velocity. And we have time as 200 seconds. What we want to know is the angular acceleration. We use the same technique to choose which kinematic equation will be best for this problem. So if our unknown is angular acceleration, we know the initial angular velocity, the final angular velocity, and time. The best equation to use will be the first one. So, as we know, our final angular velocity is 1047.2 radians per second. Initial angular velocity is 0 radians per second. And our angular acceleration is unknown, and we know time is 200 seconds. So once we solve for angular acceleration, we get 5.24 radians per second squared. As you know, we use the same methodology that we did when we were considering kinematics. All we've changed so far is the variables we're using in our kinematic equations and our considerations. So use the same method as you've done before, but make sure to compare the motions in rotation to linear motion to help make it easier for you to analyze the problems. Thank you for watching, and see you for the next video. I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what physics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you're a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website at www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.